to simplify a radical, what's the first thing you have to look at? Your chart, right? And where does this chart come from? It comes from the type of root you're doing. So depending on the type of root you're doing, depends on the type of number or chart you have to look at. This is a fourth root, which means you need to make a perfect fourths chart. That's things to the power of 4. I don't know these ones, so you're going to have to help me out with that. 16? Next one? Pardon? Thank you. What's the next one? Next one? Next one? Actually, you already did the next one. It's high enough. Okay. So you remember that simplifying a radical means to make the radicand smaller somehow. Depending on the index, depends on the type of number you look for. In this case, we're looking for perfect fourths numbers. These are perfect fourth numbers. You want to find the biggest one that divides it. So if you did 648 divided by 81, what does it give you? So by going 648, dividing it by 81, you can split the number 648 into 81 times 8. The reason you split them is because there's a rule in math that with radicals, you can split two radicands into separate radicals. So that means this thing would change from 81 times 8 to 4 through 81 times 4 through 8. Notice that both are still fourth roots. The reason that's useful is one of these is a perfect fourth, meaning that you could fourth root it. That thing should work in your calculator. It should equal 3. That gives you a coefficient, and the other radical remains the same. To be able to do like anything in this unit, you had to get good at simplifying radicals. It was kind of a requirement, a prerequisite. Everyone remembers that, hopefully? Yeah? We don't usually see to the power 4. The power 4 is usually pretty hard. You usually see a lot of squares and cubes, right? So numbers that you're more comfortable with. But it is possible you can get a giant number, and that you need to know how to work with it. All right. Adding and subtracting radicals. It's been a long time since we've done that. So to add and subtract radicals, we need to remember a couple of rules about adding and subtracting. And before Math 20, we did Math 10. And in Math 10, we learned that you can only add like terms, right? So that means x's could only go with x's, y's can only go with y's, you know, like an xy or an x squared can only go with another xy or an x squared. It just makes the sound a little bit uneven. We're going to plug it in. So the sound probably sucks, but I'm going to get better. If you look at this, it's the same type of rule. You can only add like terms. But in this case, we say you can only add like radicands. So you need to have the same thing under the square root sign if you want to add it with something else. You also have to have the same index. In this case, they all have a square root, so they're all the same index. Now, if you look, none of these are the same. And they're not even really close. So what you need to do is try to make them the same. And the only way we need to know how to change radicals is to simplify them. So we're going to try to simplify all 4 of these. Simplifying root 18, the biggest perfect square that would go into that is 9. The square root of 9 is 3. That would simplify to be 3 root 2. If you remember, you guys were getting really good at simplifying radicals, and it was coming that quick for some of us. 250 can be divided by 25. So that would change this into plus 5 root 10. Square root of 25 is 5. Root 10 is left over. Root 40. Root 40 could be divided by 4, which is a perfect number. Square root of 4 is 2, and you're left with 10. The last one is the 100, which can be divided by 100. Oops, there's a bigger one than 100 that goes into it. What is it? 400 is a perfect square. So it's 20 root 2. Remember, you always want the biggest perfect square. I almost fell for that one. So 800 is divisible by 100, which is a perfect square. But it's actually divisible by 400, which is an even bigger perfect square. So make sure you're always getting the biggest perfect square. All right, now that you've simplified them all, you go back to your original goal, which was to add and subtract them. And if you look, your black one and your blue one are like radicals because they're both square root 2's. That means you can add these together. If you have 3 square root 2 plus 20 square root 2, you have 23 square root 2's. Common mistakes people make is they would say they have 23 square root 4, and they would add the radicals too. Make sure you're not adding the radicands. Make sure you're not adding the radicands. You're only adding the coefficients. That's why I use the words, I have 3 square root 2's. I'm trying to picture it as 3 separate square root 2's. And then I have 20 square root 2's. That's 20 separate ones. So altogether, I would have 23 of them. If you look, you also have square root 10's. So you have 5 square root 10, and negative 2 square root 10. So if you were to add those together, 5 minus 2 would be positive 3 square root 10. That is as simplified as you can get when adding and subtracting those terms. Any questions about that? The big thing is, remember, you have to simplify first to be able to even add or subtract. People usually look at this and then start to panic, and they just start adding radicals and doing crazy things. Remember, simplify first, and then you're good. All right, multiplying. Multiplying and dividing radicands works a lot the same as adding, subtracting, and multiplying and dividing variables. We used to say numbers go with numbers, letters go with letters. Right? So if we were to multiply two things, we don't need to write this down. But if you were to do like 2x times 3x, you would go numbers with numbers. 2 times 3 is 6. X times x would be x squared. Letters with letters. Those rules still apply, except now you learn that numbers go with numbers, letters go with letters, and radicands multiply with radicands. Okay? That means when we see a question like this, we follow all the same steps we've ever done. Binomial times a binomial is best done using an area diagram. You don't have to use an area diagram, but it's definitely what you guys are best at, which is why we do it. In that area diagram, you fill in each space. When you're filling in each space, you go numbers with numbers. In this case, it's now coefficient with coefficient. So 3 times 2 is 6. And then you do radicands with radicands. 2 times 5 would then become 10. Notice that it's still a square root. It's not a 4th root or a 5th root or something crazy like that. The index stays the exact same. Next one. We go numbers with numbers. 3 times negative 2 would be negative 6. And you do radicands with radicands. I have a root 2 on this one. I have no radicand on the other one. So that means it's like doing root 2 times 1, which would just be root 2. If there's no radicand to multiply by, you're just multiplying by a 1. There's nothing there. You should be able to do the next two pretty quickly. So this one should become negative 2, because it's a negative sign and a positive 2. And then it's an 8 times a 5, so that should be root 40. The last one should just be, nope, it would be positive 2. 2 root. You then take everything from inside the area diagram and you write it all out. So that means I have 6 root 10 minus 6 root 2 minus 2 root 40 plus 2 root. And that, if that was a written question, which we will have written questions on your midterm, would be half a mark. That gets you halfway. Why would it only get you half? Exactly. You can simplify and add like terms. If you're looking at your radicands right now, root 10, that's good. That can't be simplified. Root 2, that's good. It can't be simplified. But root 40 and root 8 can both be simplified. They can both be divided by perfect square numbers. That means we need to change those. So this will be 6 root 10 still. This will be 6 root 2 still. This one. Negative 2 root 40. The square root of 40 can be divided by 4. Square root of 4 is square root of 10. Right, I'm just doing it on the side. The square root of 4 is equal to 2. Square root of 10 remains the same. The reason I'm doing this one on the side is when you're simplifying radicals that already have a coefficient, you end up with 2 coefficients. When you have 2 coefficients, what do you do with them? You multiply them. So this would become negative 4 root 10. You multiply them together. The last one, I have 2 root 8. So root 8 can be divided by 4. That would give me another coefficient of 2. 2 times 2 would give me 4 root 2. Remember, when you already have a coefficient, you multiply it by whatever your new coefficient is to get your final coefficient. It's great that we simplified them, and just like Jackson alluded to, you're going to end up with like terms. You have 6 root 10 minus 4 root 10, that's 2 root 10. Then you have negative 6 root 2 plus 4 root 2, you end up with 2 roots. That would be an answer that would get you 100% on a written question. Oh, sorry, negative 2 root 2. You're definitely right. All right. That's multiplying radicals. Dividing radicals. Usually, when we see a radical on the bottom, we do something called rationalizing, which would get the square root off the bottom because that's against our rules. But there's actually an easier way to do some questions, and only some questions. The easier way to do some questions is to recognize that the coefficients can all be divided by a certain number. So in this question, all the coefficients can be divided by 5. So if I did 15 divided by 5, I'd get 3. If I did 5 divided by 5, I would get divided by 1, which you don't need to write it. The next thing, and the trick that's really useful, is recognizing if all your radicands can be divided by something. In this case, I have root 10 and root 2. So what can both of those be divided by? 2. 10 divided by 2 would give me root 5. 2 divided by 2 at the bottom would be root 1. We don't need to write out root 1. So dividing radicals can be very easy, but only in special circumstances where things can be completely divided out. It's very rare that happens. Every once in a while. Any question about multiplying or dividing? right? This is, actually, sorry. If you forgot that trick, and you looked at something like that, and you wanted to get the square root off the bottom, because remember when you're simplifying radicals, you always have to get the square root off the bottom? The other way you would do it is by rationalizing the denominator. Who remembers what rationalizing the denominator is? Yeah, that's where you're trying to get the radical off the bottom. So what you do is you times the top and the bottom by whatever radical is on the bottom. So in this case, you'd be times it by root 2 and root 2. What that does is it gives you 15 root 20 on the top, divided by 5 root 4 on the bottom. The reason why rationalizing works is it'll always end up giving you a perfect square on the bottom that could be square root. The square root of 4 is 2. It'll always work that way. So it ends up that the square root basically just cancels itself out. That means on the bottom I actually have 5 times 2, which is 10. That's how you would rationalize, and then you would have to simplify if you could. So by looking at this, I can definitely simplify root 20. Root 20 can be divided by 4 to become 2 root 10. If I have 2 coefficients, 15 and the 2, they multiply together to be 30. The root 10 remains, and the divide by 10 remains. The last step when you rationalize is to check to see if your coefficients can both be divided. In this case, they can. My final answer is 3 roots, which that's definitely a longer process to get it done. But sometimes you have to do that, especially in a situation where laughing, I don't know why. It should be root 5. It's fun and take it, you know how. There we go. It's definitely a longer way to do it, but it's actually how you have to do most questions. The reason being is that usually you don't get numbers that can divide into each other. Yeah.
This isn't when we do a conjugate, right? Conjugate is when there's a binomial on the bottom?
Correct. The other thing is rationalizing only works for monomials in the denominator. The next question, you can't do that trick. Okay? Because this is a binomial on the bottom. Now, I'm going to purposely make a mistake. I'm going to show you why it doesn't work. Okay, so you don't need to write this down. The reason why rationalizing doesn't work is if you did root 2 and root 2 on the top and bottom. On the top, you'd end up with 3 root 2, which is great. On the bottom, remember when you're multiplying, this bottom is in brackets. So that means you end up with 5 root 2, and then minus 2 root 4. This one is going to go away, but this one isn't. That's why when you have a binomial on the bottom, rationalizing doesn't work. The square root of 4 can simplify, but the square root of 2 can't. And now you still have a radical on the bottom. And you just end up getting back in that same cycle over and over and over again. And you'll never be able to rationalize away a binomial. Instead, what you do is something called a conjugate. Remember the word I can't spell but we use all the time? Starts with a C, I'm pretty sure. And then there's a J or something in there. Yeah, that one. So it's G. Yeah, see, I don't even know what it is. A conjugate is the same binomial, but with an opposite symbol. So it would be 5 plus 2 root 2. So a conjugate is the exact same binomial with an opposite sign. You then want to do the same thing to the top.
Yeah.
When you do this, put in the work to properly multiply these things together. A lot of people just try to skip and try to remember little tricks of how they think it should end up, and they end up making mistakes. Okay? Put in the actual work, take the 3 and actually distribute it in, or do an area diagram, whichever way works for you. Right? So this thing should become 15 plus 6 root 2. So the 3 only multiplies by the coefficients. On the bottom, you should do an area diagram. 5, negative 2, 2, and then 5, positive 2, root 2. You have 25, negative 10, root 2, positive 10, root 2, negative 4, root 4. Like, actually go ahead and do the area diagram, put in that work. It's worth it because it makes it more consistent for you. It also helps you remember just how to do the proper steps of multiplying. Whenever you try to skip steps and just think you know what's going to happen and you're trying to use tricks, you're forgetting what you're actually supposed to be doing. And you're forgetting the actual process, which hurts you in the long run usually. In this case, you should recognize that 2 of your terms cancel out. Conjugates always do that, right? That's why conjugates work. Is the root 2's cancel each other out because they both have the same coefficient but opposite signs. That means what I'm left with is 25 minus 4 root 4. The root 4 can be simplified. The square root of 4 equals 2. 2 times negative 4 is 8. So I have 15 plus 6 root 2 divided by 25 minus 8. 25 minus 8 equals 17. He says, unsure of himself. And that is a simplified radical because the root sign's off the bottom. That is good. If you remember, we very rarely ever actually had to do conjugates. We did a lot of rationalizing. We didn't do a lot of conjugates. It was a rare circumstance, but it does happen every once in a while. In Math 30-1, it was like 3 years ago. We were doing a diploma review set up by somebody else to mimic the diploma exam that was coming. I think it ended up being like a field test. So it's like the government sends out tests and then they survey the answers that you get, and then they either use the question on the diploma or they don't use the question on the diploma. And there was a question on there which you had to do the conjugate before you could solve the entire thing. It was crazy. And most people, actually everybody, including the teachers, which was me, forgot how to do a conjugate or even what a conjugate was. And yet we teach it in grade 10 or 11. So like it's very rare that it happens, but it is something you just need to be aware of. And that has haunted me ever since. Because it was very embarrassing to be like, I don't know how to do this. And they're like, just do the conjugate. And I was like, oh, I feel stupid. So now you know. You'll probably get like one of these on your midterm. You'll probably get one on your final too. Yep. Same length as any unit test. So it'll be like 20-ish questions. I think it's broken up like 7, 7, and 7 or something like that.
I thought it'd be like 75 and something like that.
No, it's short.
60. I thought it was going to be like 60.
What was last year?
All right. Simplify and state the restrictions on the variable. Simplify. Simplifying has to happen after you state the restrictions. So restrictions are the first thing that you do. Remember, restrictions are things that variables are not allowed to equal. In math, you're not allowed to square root negative numbers. So that's why you end up with restriction. Because if I was to look at this right here, square root of x is fantastic, but x actually has to be a number. And there's certain numbers it can be, and there's certain numbers it can't be. We know, for instance, it can't be negative 6, right? Square root of negative 6 is impossible. It can't be negative anything. In math, we represent that by saying x is greater than or equal to 0. So that is a restriction. It's saying the number has to be bigger than any negative number. Yeah.
The restrictions, you always look at what's on the root.
Exactly. So you do it again. So now you have to look at this one and say the same thing. I know I can't square root negatives. So in this case, that means 2x has to be greater than or equal to 0. You then take whatever's under there and you write it out like that, and then you have to get x all by itself, so you divide both things by 2. So in that case, x has to be greater than or equal to 0. You notice both restrictions are the same thing. They both end up being x is greater than or equal to 0, so that's your restriction that you use. Yeah.
How can it be greater than or equal to 0 if it can't be 0?
You can't square root 0. So the square root of 0 is just 0. So that's why it's allowed to be equal to 0. Good question is that will it always be that they're the same? It won't always be that they're the same. So it's possible that one of yours could be x greater than or equal to 0, and one of them could be x has to be greater than or equal to 3. Whichever one is more strict is the one you have to do. So for instance, this one is more strict, meaning that every single number in the green one would still follow the rule in the red one. But there's some numbers in the red one that wouldn't work in the green one. For instance, the number 1 is greater than or equal to 0, but it's not greater than or equal to 3. So you always choose the more strict restriction if you have more than one. Alright. That's how you state a restriction. You take whatever's under the root sign, make it greater than 0. That's all you have to do. Now, sorry. You could. That's a good question. Why doesn't it add restrictions? Oh, this one should say restriction. You could have restrictions. So if you had the letter Y or something, you had a different letter, then you'd have to have a restriction for that letter as well. So for instance, if I had like a root Y, then I'd also say, okay, Y has to be certain. It has to follow a certain rule. So every letter in a question should have a restriction that comes with it. In this case, the only letter we have is X, so it had to be greater than 0.
Aren't some restrictions written as like separate notation, or is that only for something else?
Yeah, like you could take this, and you could also like tag on to it, like X has to be greater than or an element of the reals, and then you could do the whole set builder thing. For the most part, we just see this part now. We can kind of shorten it because it just gets so long, right?
Yeah.
But as long as you understand what it means, if they do put it in step builder notation, you're good.
How did you get the whole greater than or equal to 3?
I just made that up as an example to answer Amanda's question. Yeah, because she said, what if you have more than one restriction?
Oh.
That's what you would do if you have more than one restriction. You would take the stricter one. So I made one up in green.
It's actually 0 though.
Yeah, that's not a real question. Yeah. You only flip the sign if you're dividing by a negative number. So if that was a -2, we would have flipped the sign. All right, simplifying. I want you guys, actually, no, we'll do that since the first one was multiplied variables. So our restriction was x is greater than or equal to 0. Now, we need to simplify this thing, which means multiply it together. When you multiply it together, I recommend doing an area diagram, since you're fast at. Some of you are good at distribution, and you can do that as well. As long as you follow the rule that coefficients go with coefficients, and that radicands go with radicands, you should be good. this is how an area diagram would look for a monomial times a binomial. It's just a smaller area diagram, right? The less terms there are in the question, then the smaller area diagram should be. The more variables the questions are, then there should be bigger area diagram. Just kind of makes sense. To do this area diagram, we're going to follow our rules. Now, coefficients with coefficients, that becomes -6. And then radicands with radicands. In this case, now we have letters as radicands, so variables. That's when we go back to our Math 10C rules, which would be numbers go with numbers, so the 2 would still be the 2. And x times x would create x. You then fill in the next spot, which would be radical or coefficients with coefficients, so -3 times -3x would be negative, I'm a liar, positive 9x. And then the root x would still just be a root x. Numbers with numbers, letters with letters. Outside of the root signs go together, inside of the root signs go together. You then take whatever is left over and you write it up. That, really well done, not completely. The reason it's not completely done is because you can simplify one of the radicals. This one can be simplified. The reason it can be simplified is, remember that if you have things multiplied as a radicand, you could break them up. So this thing really could be looked at as root 2 times root x squared. What would the square root of x squared be? Just x, right? So that means this could have simplified to turn into an x. That's one way to look at it, okay? And that's how some people like to view it, is they remember this trick and they break it apart. The way that I like to do it is when I'm simplifying radicals where there's a variable underneath the root sign. I look at the index, which is a 2, and I ask myself, how many groups of 2 could go into x squared? So how many groups of 2 could go into 2? One group. That means one x comes out, and how many x's would be left under the root sign? None. So I would be left with x root 2. And the -6 that was originally there as a coefficient would still be there as a coefficient. That's how I like to do it, because when the numbers get really big, it helps me remember how to simplify things. When the numbers are small, like just an x squared, sometimes it's easy to just remember. But when it's like x to the power of 7, it can get a little more challenging. Yeah. Yeah. So you ask yourself, how many groups of 2 could go into the exponent 2? The other one then says plus 9x root x. Both of these have coefficients that include an x. But they don't have radicands that both have an x. So can these be added together? They cannot, because the radicands are different. They're not like terms. The coefficients are like terms, and that's good, but you need the entire thing to be like terms, and those are not. So you cannot add those two terms together, because the radicands are different. This would have been your final answer. We have 6x root 2, and then plus 9x root x. The restriction on it was x is greater than or equal to 0. All right. There's one here. I want you to give it a shot. See if you can do it on your own. I'll put my work on the board so you can check your answer. But we just did one similar to this. It's a little bit harder, but give it a shot. See if you can do it. So to simplify this thing, I did an area diagram. You don't have to do an area diagram. I don't know if anyone in here would have distributed that, but if you did, I mean, it still works the same as long as you follow the rules, coefficients with coefficients, radicands with radicands, right? It's the exact same. It's just making sure you follow the actual rule that we're learning. The method can change. The big thing here is remembering that x to the power of 1 times x to the power of 5 is x to the power of 6. So remembering to add your exponents together. That gets a lot of people. The next thing is remembering how to simplify radicands, which you ask yourself, how many groups of 2, because the index is 2, could go into 6? I could get 3 groups, so it becomes x to the power of 3. There would be none left over, so that means there's no more radican with an x in it. Does that make sense? Yeah. And you could also think of it as division, right? That's all division is grouping. So if you had 6 divided by 2, it equals 3. The problem is the remainder throws people off. Yeah. So if it was x to the power of 7, then I would have had x3 root x, because there would have been 1 left over. That wasn't an improvement group. All right. Solving radicals. There's a bunch of different solving radical type questions. This is one where you only have one radical sign. If you only have one radical sign, to be able to solve it, you need to get the radical by itself. In this case, the radical is isolated. It's by itself, and then everything else is on the other side of the equal sign. If you were to chop this thing in half, this, see where the equal sign is, everything else is on one side, the radical is on one side by itself. Isolating a radical. The reason you have to isolate a radical is the way you get rid of a radical is to do what to both sides? Just square it. If you square both sides, it'll cancel out the square root sign. Whoa. That gives me x plus 3 equals 4. Then you can move things around as need be. Let's subtract 3, mean x equals 4. And that's how you solve a radical. Get it all by itself on one side, square root both, or square both sides to get rid of the root. It should be like one of the easiest things that we do in this class. On our unit test, it didn't end up being that way for some reason. But it's really that easy. You guys have been doing it for, honestly, like a couple of years. You've done it back in Math 10 and Math 9. So I have faith you can do it. It does get a little bit harder when you have something like this. The reason this is a little bit harder is because when you isolated your radical, you ended up with a binomial over here. And what people typically forget is that when you square both sides, that means this has to be in brackets when you square. That's what throws people off. So remember that it has to be in brackets to actually do this question. That means it gives me x minus 1 equals x minus 7 squared. The next thing people forget is that a binomial squared does not mean what I'm about to do. You don't bring the squared in. The reason you don't bring a squared in is something squared means you have 2 of that thing. That's where you scratch out the squared and write the binomial again. That means you have to do an area diagram, which is going to give you an extra term. If you just brought the squared in, you would be missing that middle term. When you do the multiplication of this thing, you should get x minus 1 equals x squared minus 14x plus 40. So you need to area diagram those two binomials together. That makes isolating for x even harder. The reason it makes it harder is because you have an x squared term here. That means you have a quadratic. You don't have a linear equation. You can't just get x by itself. How do you solve things that are quadratic? This is a little bit of unit 2. You need to factor, but before you can factor, you need to be in general form. So you need to move everything to one side first. So you have x squared minus 15x plus 50. So subtract an x from both sides, add 1 to both sides. Subtract an x from both sides, add 1 to both sides. Now you can do your factoring to try to solve this thing. If you factor the blue thing, you end up with 0 equals x minus 10, x minus 5. Your solutions are then the zero product property, with x equals 10 and 5. Yeah, that's diamond method. Yeah, we always call it diamond method.
I don't know why.
All right.
Did you also graph that?
No. Yeah, you could graph this.
Yeah.
Once you get to the quadratic, remember you could use quad formula, you could box method, or you could graph it and find your x-intercepts. So you actually have 3 or 4 different methods now that you can use to solve it. Now, I don't want the focus to be on the solving in this case. Okay? The reason why is because we haven't really looked at solving quadratics yet. We're going to review that all day tomorrow. Instead, what I want you to focus on is something called an extraneous root. Who remembers what extraneous root meant? Yeah. Like mathematically, you're correct. Like you've solved it correct. But then one of your solutions might not actually work. Now, there's 2 ways to check if it worked or not. Way number 1 is to put those equations back into your original equation and see if it actually worked. Way 2 is to create a restriction and see if it fit your restrictions. In this case, if you put it into your restrictions would work. So you still need to test it to see if they both work. The way we test our solutions, you take each answer, or let me move off to the side, 10, and you replace it back in the original equation. So the square root of 10 minus 1 should equal 10 minus 7. So I took the original question and I changed x to be 10. 10 minus 1 is 9, so root 9 has to equal 3, because 10 minus 7 is 3, and that is true. 3 does equal 3. So 10 is a good solution. If you try out the number 5, you're going to have square root of 5 minus 1 equals 5 minus 7. 5 minus 1 is 4, so root 4 has to equal negative 2. Square root of 4 equals positive 2, not negative. So that means 5 does not work, it's extraneous. I was like, someone's gonna ask that. I didn't see any hands right away, so I was a little concerned. Now let people write that down. They're going to answer your question. So Amanda's question was, when you square root, you should get a positive and a negative. Correct? So the square root of 2, or square root of 4, is equal to 2. That's 100% true. When we do positives and negatives, is when we're adding the square root sign. So for instance, when you had something like, you don't need to write this down, if you had something like x squared equals 4, and you were creating the square root sign, that's when you added the plus minus symbol. But it's only when you were creating the square root sign, when you added it into the question. the square root sign was always a part of this question, which means they were only doing the positive root. Yeah, for sure. Yeah.
And then we still have to do positive, negative, not any root signs.
Yeah, so anytime you're doing the square root, whenever you do something like this, no matter what unit it's in, you always put a positive negative. It doesn't happen very often in the unit 1. It doesn't really start to happen until unit 2. And the reason being is unit 1, the square root sign was already always there for you. And it was always a part of the question. Where unit 2 is when we actually started square rooting things and adding the square root signs in the questions. All right, this is the start of unit 2.